Welcome to the lecture on optimization and smoothing. This is the first out of 2 lectures on this topic, and we will focus on nonlinear least squares problem. We're going to build up to understanding a class of problems that we can solve using a nonlinear least squares solver called Gauss-Newton and its extensions. We're going to establish some notations. We say a matrix is positive definite or positive semi-definite if you see this notation that A is greater than B. That means A minus B is positive definite. Now it's curly bracket. Maybe you just use the, curly inequality. You can use just normal notation as well, inequality. It doesn't matter. So that means that A minus B will have positive eigenvalues. The 2 norm, which is the Euclidean norm, we can show it with this notation, just a plain norm notation, or maybe you put 2 in the bottom, which is the same thing as taking the dot product or x transpose x and taking the square root of it. L1 norm is sum of the absolute values of a vector x. This is also called L2 norm. This is called L1 norm. In general, LP norm is calculated by raising the absolute value of each entry of the vector to the power of p, and then raising the sum to the power of 1 over p. And the dot product or inner product, any of these notations mean the same thing. And the norm ball is a neighborhood centered around xc less than a radius r, if you see this notation. Now, generally, you can define the ball using any of the norms you want. It doesn't have to be the Euclidean norm. But if it's not stated, the default notation is the Euclidean norm. We're dealing with an objective function that takes a vector in Rn and gives you a real value. The argument of this objective function is called a decision variable or design variable. We wish to minimize this objective function and find the value of x that minimizes the objective function. So then x that minimizes f is our solution. If the solution we find obtains the least amount of value for the function in the entire domain, that's a global minimum. If it's in a neighborhood, we call it a local minimum. For example, here we have local minimums, and we have local maximums. This is the global maximum. And this is, of course, the global minimum. We're going to need some structures that we can calculate for continuous functions. In general, we assume the objective function is smooth and continuous. That means we can differentiate the function. The first derivative of the function, which is a vector, it takes a vector and gives you a real number as the output. Therefore, when you calculate the derivative, this is called a gradient, which will be a vector of partial derivatives of the function. Now, sometimes this is a row vector, but if you're working with column vectors, you can stack them in a column. It's not that important. That's a choice that you can make. But if you strictly want to follow the definition that will show up in the Jacobian, this is a row vector. But we tend to work with column vectors. So the gradient is a vector of the same size as your domain, x. So this is an n by 1 vector. Or sometimes we write grad f. Hessian is a symmetric matrix of second partial derivatives. It's symmetric because because of the assumption that the function is continuous, approaching the derivative of the derivative, right? This is a second order derivative. Hessian is the Jacobian of the gradient. So approaching the derivative of the function in different orders should give us the same answer. Otherwise, it violates the condition of differentiability at that point. Therefore, by assumption, this must be satisfied, and Hessian is a symmetric matrix. And the diagonals are second derivatives for the same variable. Now, using Taylor's theorem, we can approximate a continuously differentiable function, an analytic, that means up to the order we want, all the derivatives exist, and locally will converge to some functions. It's not going to explode. The derivatives exist, and we have convergence. So we can approximate our function using a polynomial. And the way it works, that the first part is the linearization of the function. We are writing the expansion about x using a delta that we call d. So the approximation of the function has a linear term, which is f of x, plus the gradient transpose times d, which we talked about this sometime, that this, in fact, is the differential of your function. And what it's basically saying here is that my function up to first order, if I move a delta at x, is the value of the function at x plus a differential, a delta in the function. And this differential, of course, is in the infinitesimal sense, calculus, which is exact linear movement. Similarly, we can talk about the second order polynomial approximation. Then, of course, the second order derivative will show up, and that's the Hessian matrix. Then we can have a quadratic approximation of the function up to having the second order derivative here. And then we can drop the higher order terms. You can generally do this up to any order, but it's very complicated to calculate third order derivatives and higher than that. We are talking about Rn and Euclidean spaces. Generally, if you come across works that deal with manifolds and curved spaces, this notion of inner product will change. So the gradient, in a lot of contexts, is called Riemannian gradient, because the metric will give you different directions based on how the space is curved. But we're going to deal with Euclidean space, flat spaces. This is the usual calculus we all know. So the local quadratic approximation of the function can be written like this. We will need to calculate the gradient and the Hessian. Sometimes you see this form, which is a change of variable. F of x around x0 is f of x0 plus gradient times a delta x, right? Both are fine. Depending on what you want to do, you might prefer one notation or the other one. So from calculus, the first order necessary condition to find the extremum of a function is done by setting the gradient to be equal to 0. So the first order necessary condition is this. Find the roots of the gradient. The second order necessary condition is that the Hessian be positive semi-definite. Because we want to find the minimum, the eigenvalues of the Hessian being non-negative means that we have convexity in a local neighborhood, and that leads to a minimum. If it's the opposite, it's negative definite that corresponds to a local maximum. But we always minimize. If we want to maximize, we just multiply the objective function with a negative sign. The second order sufficient condition is when all the eigenvalues are positive. Okay? And if you have mixed signs, that's a saddle point, and it's generally not a good situation because we know that's not, there's a solution better than that. We already know that. The test is inconclusive. You can go to higher order derivatives. There are more tests. You can find out what direction you should move. But fortunately, we're not going to talk about those stuff. So another structure is convexity. If we do come across an objective function that is convex, the local search will give the global solution, and that's very desirable. However, we will see that nonlinear least squares in general might not be convex. Sometimes it is, sometimes it's not. So the function is convex when you pick 2 points and interpolate using a theta parameter. That line is always above the function. In other words, if you pick a point and linearize your function, the line is always below the function. It's never the case that the line intersects your function. In general, a set is convex. If you pick 2 points and connect them with a line, the line never leaves the interior of the set. That's the convex set. So this condition is the same thing as if you linearize your function, the value of your function is always greater than or equal to the line that you approximated at that point. And the second order condition for convexity is that the curvature, the Hessian is also showing geometrically the curvature, these eigenvalues are non-negative. We have positive curvature, which causes to have this bowl-shaped and convexity. So the first problem we should talk about is the linear least squares before we make it nonlinear. Because the nonlinear methods often solve a linear subproblem and they iterate due to linearization. So if we can solve the linear case, then we can come up with an idea to solve the nonlinear problem using linearization. So a linear least squares problem is generally a problem that you have a linear system, AX equals B. A is a tall, skinny matrix, more rows than columns, and full column rank. That means all the columns are linearly independent. These are the assumptions. In practice, B is never in the range of A because of noise and all the imperfection in the data we observe. And generally speaking, this corresponds to the measurement, and this is the model. You remember in the Kalman filtering, we had Z equals HX. So that matrix A is the model, is a sensor model in this context of perception and state estimation. Or it could be an assumption, but it's a model that we assume. And the vector that is the right-hand side of AX equals B is something that we obtained by sensing. So because of this imperfection, we define a residual, which is the difference between model and the measurements. And then we aim to minimize the norm squared of this residual. So the residual is a vector. You take the Euclidean norm. It's the sum of squares of each term, and then you basically minimize that, right? Because norm takes the square root. When you raise it to the power of 2, you drop that square root. So basically, this is 1/2 sum of R1 squared all the way to R, how many? It's a question for you. N or M? N? N or M? You need to say louder. M? Okay, so A is a map from Rn to Rm. So R will be m-dimensional. Right? A is a map from that acts on a vector that belongs to Rn and gives you Rm. So the gradient is, we just go ahead and calculate the gradient of this quadratic term. If you don't know how to do it, you can Google matrix calculus. That's a website. You type your objective function, and that will give it to you. So the gradient is A transpose times A times X minus A transpose B. The Hessian is constant and is quadratic, A transpose A. If all the columns of A are linearly independent, of course, will be positive definite. So if we look into the first order condition, symbolically, we can write the solution as A transpose A inverse times A transpose times B. And the second order condition is telling us that by assumption that A is full rank, this is positive definite, therefore it is invertible. In other words, you can say that the determinant of A transpose A is not 0. And because it's quadratic, the eigenvalues are always non-negative. Then we arrive, set this equal to 0. This will give you the normal equations. So the normal equation is from the necessary condition. We do not invert A, and we solve this using 2 methods, usually. Cholesky factorization by factorizing A transpose A, because Cholesky requires a square symmetric positive definite matrix. Or we can directly factorize A using QR. So this is a global minimum because the sufficient second order condition is satisfied for this problem. Example. We had an example of target tracking. We used different filters to solve this problem. The filters, of course, were solving the problem recursively in time. You can make least squares recursive as well. The linear case will give you the same solution as the linear Kalman filter as you verified in your homework for a problem. We are talking about a batch solution. We have the entire data, and I want to just solve one least squares problem given everything to compute the trajectory. And because I have all the information, the future information can be used to correct the past estimates. And this is the smoothing problem as opposed to filtering. Hence, we call this a smoothing. So smoothing is usually in form of optimization, or at least a window in time that processes data. So target tracking using smoothing, we deal with, it's the same problem. We have a linear motion model, because we don't have any knowledge of the target, how it moves in the plane, the measurement model is linear. We get directly 2D coordinates of the target. So you have to formulate your residual and then you can stack all your residual for one time step, and then you just stack them for all the time steps. When you do that, you construct a linear system. They will end up being in form of that AX equals B. Now, X is here X0, X1, Xn, whatever is the number of data. So the variable that you see, the long vector, is the entire trajectory discretized at different time steps. This is a simple problem, but the exact same thing will happen in Islam. It will just get more complicated because at every time step, we have a pose. Then we might be dealing with position, orientation, possibly some other parameters. So the trajectory is discretized at particular time steps. We stack them, and we want to estimate, recover the entire trajectory.
Why do we define R1 as the difference between the position of two time steps? Is that just to kind of extract information as to what the motion model?
Because in general, we have xk equals f of x k minus 1. Right? So the difference is the residual. Noise is zero mean. What I'm doing, I'm actually taking the expected value. That's the mean. So the noise is zero mean. Okay? And the measurement difference is in a similar fashion we did in filtering. Basically, the innovation term here, we call it residual. So in the filtering, we would predict, in the context of Bayes filter, predict and correct. Here, we just stack everything. We treat the motion model as another form of, you could say, observation, data. But it's a different type of observation. Usually, it's not perceptual. It's not from the environment. It could be an assumption. It could be a model. It could be a prior. Maybe it's IMU. It's usually in form of proprioception. Here is an assumption, right?
Repeat again, how do we formulate it from R to AX equals B?
How do we formulate it from R to A? That's the good question. That's why you should look into my code that I provided. But generally, when you stack all these residuals, if I do it only for these two, what is my state? I don't have a space. So the motion model is telling me that I have negative of identity and identity. The observation model is telling me I have zero and H. The right-hand side is supposed to be zero. And this one is supposed to be the measurement. Okay? I only have 2 variables here and 2 equations. Typically, for 1 equation, we get one from motion model that correlates the variable with in 2 time steps, and the observation is for 1 time step. And then we stack all of them. This will grow, right? It's not going to grow just in number of rows, but because we add more variables, the columns will grow as well. Does that answer your question?
What should we expect for a result? So if we can have stacked all those information from measurement, then what is the expectation for when you do a smoothing problem?
We want to solve for this vector. That's the goal. Right? The same goal that we had when you implemented the Kalman filter. Right? So the objective is to find the design variable, decision variable, the state variable. They all mean the same thing. Now, we recognize that this is a linear least squares problem because it leads to ax equals b. If you solve it, it will nail the trajectory, and it will be smooth. It won't be jumpy because we just solved everything all at once using a linear least squares, which in MATLAB or Julia, you just, once you form A and B, X is basically A backslash B. That's all you need to do.
So it's kind of a big question, but so in Robotics 1, kind of towards the end, we saw something that looked very similar to the previous equation, to the most recent equation that you wrote in the like linear programming portion. So is it kind of like is linear programming a method that is used for?
No, we are not talking about linear programming here. Linear programming, we could, but it's a little off topic at this point. That's the problem of having a linear objective function and linear constraints. We're talking about unconstrained problems. Now, I'll point out one of them is actually constrained, but we can convert it to the way you see I'm doing it. But this is the context of unconstrained programming, optimization problems. Linear programming is the first, usually entry-level topic to constrained programming. There is a course, it will be taught in fall, IOE, I think 611, by Professor Fatai. I highly recommend that because he's an expert in that area. He will teach you nonlinear programming. He will talk about linear programming, quadratic programming, convex programming in general, generalization of that, STPs, semi-definite programmings, when you deal with matrices. We're not talking about those stuff here. So if you stack all the variables, as you see, we have 400 lines, rows for the matrix, and 200 variables. So 200 variables because each variable has 2 coordinates, right, in the plane. It's like x1, x2. And I have 200, so that means it's 100 steps. This is 100 times steps. When you visualize the matrix, you realize that this is a sparse matrix because the total number of entries is 400 times 200, which is 80,000 entries in this matrix. That's a large number. However, only 604 of them are non-zeros. Everything else is 0. So it's a tiny fraction of this matrix that contains information. The rest is just placeholder for making sense of that matrix representation of the equation. So we usually do not construct this matrix explicitly by filling in zeros. You can use the sparse matrices to only fill in the non-zero terms, okay? That will be very memory efficient. A transpose A preserves the sparsity, although you can get many patterns here. Because it's a simple problem, it's band diagonal. It's not only diagonal, it has a thickness here. So it's a band diagonal matrix, and it's a sparse. When you factorize A using QR, this is the upper triangular matrix that looks almost diagonal. Also, when we factorize Cholesky, the L transpose has a similar form. Now, in Islam, you will get more interesting patterns of sparsity. The shapes will be more interesting. This is because it's a simple problem. We don't have basically connection between a variable at time step 10 between a variable at time step 1. So there is no non-zero entries in this A transpose A, or the A matrix. In Islam, because of the loop closure, suddenly you get non-zero terms here, right? Because variables at totally different time steps can get correlated. The sparsity pattern will remain, and that's a very important factor in solving the problem efficiently. Why? Because factorization of any of these matrix factorization, roughly, if we ignore the small differences between different methods, they scale cubically. When it's sparse, usually we can do it in linear time. When in this level of sparsity that I'm showing it, it will be linear in time.
Question that, what's the median to apply those?
Non-zeros. So I have a matrix, right? 1, 2, 0, 0, 0, 0. I make a plot out of it. You have columns, you have rows, right? You have, well, this is not like this because this is my 0, right? Or 1. So I have a dot here, a dot here. I don't have dot anywhere else. In MATLAB, you can use a SPI function to visualize this. There should be a similar function in Julia and Python as well. So we don't care about the values as long as there is something in that entry. A more interesting example that they might teach you in machine learning courses, linear regression with L2 regularization. We're given a data set, n data points. The data points are in form of the inputs and the target values, or measurements. xi can be a vector of Rn in general, and the target values are, in this case, scalar. Because the target values are continuous, the outputs, we call it regression. If they're discontinuous, it's a classification problem. Now, we want to build a linear model, so we assume a structure for the model. The function that we want to approximate is of this type, which is a weighted sum of some basis function. If it's linear basis, this would be like this. Basically, we're trying to feed a line or plane. But that's not interesting because data might be nonlinear, so we use nonlinear basis. It is still called linear regression because the function is linear in weights. Weights are the unknown variables. The basis function, although they're nonlinear, we will evaluate them, there will be just numbers. So the function y has this form. So it's a function of x if we know w. Therefore, if we know weight for any new input x, we can evaluate the function. So we constructed the model of the function. But we don't know the weights. But we're given data. From data, we want to estimate the weights, w. So we can write this also this way or any way you like. They all mean the same thing. So the W itself is a vector of stacked individual weights. So we have n data points, right? And we construct the function that the function makes every input a basis, which you can assume if we can see that if we have 1 million data points, of course, we're not going to use this method. So we have W0 to Wn. And similarly, phi is a stacked vector of individual basis functions. Typically, we choose the first basis 0 to be 1. And because of that, W0 is called the bias parameter. Now, if you're truly dealing with linear basis, let's say it's a 2D example, right? This 2D example, linear basis, this is a line regression. Linear, in 3D, this will be plane regression. So if you don't have bias, all you can do is finding different lines that go through the origin. So without bias, there will be no fitting to data. So you will need the bias so you can learn actually what's going on in the data. Now, this gets a little blurred once you make the basis nonlinear. You can still recover that because somehow the optimization can figure out to make one of them bias, or mixture of them can shift it to a different place. In any case, it's customary to include still the bias term. So the first basis is 1. You can have many options for the basis. One default model that people use is the Gaussian or a squared exponential basis. In the context of neural networks, this is also called radial basis functions, RBF kernels. So it's the exponential of negative of difference of input x with the center of this bump or Gaussian shaped basis divided by some bandwidth. This is the kernel bandwidth. That means beyond that certain region, it will be 0. So the bandwidth controls how wide this basis is. If it's small, the influence of the basis, of course, is in a small neighborhood. If it's too large, all the bases will get mixed up. And this is called, S is called hyperparameters because it's not directly the parameter of the model. W is the parameter. And this is a parametric model. So we want to solve this using least squares. So given that we have the bias term, we have n plus 1 data weights, although we have n data points. So this will be underdetermined because we have n plus 1 variables, n measurements. So the truth is that this will be a minimum norm problem. That means we should minimize norm of W subject to this linear constraint. But the equivalent problem using method of Lagrange multipliers will be this regularized problem. So it's customary to, in machine learning literature, to just write down the regularized least squares problem. This term is called regularizer. You can choose any regularizer that you want. The role of this is that to enforce the search to find the smaller weights that will satisfy the main objective, okay?
Oh, so this is different than the lambda that's typically used for like reducing overfitting.
Your question is too broad. Is lambda is used for reducing overfitting? Yes, it can be, because it's a trade-off. Yeah, it's a concern. You don't want to overfit, so we have to find a good value of the lambda. So we can stack these individual terms into a matrix. Now we have a linear system, and it's also regularized using L2 norm. And the matrix phi is called design matrix. It's an n by n plus 1, because each row is basically 1, phi 1, x1, phi n x1. So we turn every input to a center of a basis function, and for every basis, we evaluate it using all other points, including itself. That will lead to this design matrix. That's basically your A matrix that we had. How to solve this? Well, this is all smooth and nice. It's a quadratic cost function. Take the gradient. It will give you phi transpose phi times W minus phi transpose T plus lambda times W. So those 1/2 are included to keep the gradient pretty. Use this first order necessary condition, you get the solution. Again, of course, we won't invert it explicitly. So it's interesting that when you regularize, your normal equations takes this form. As opposed to not having this extra term here. So the role of regularizer is doing this. Changing the left-hand side of the equation. We'll talk about it more. More on the effect of this will come later. Now, I have a code example for you. You can look into it. But what's going to happen is that given the training points, we use them as basis. I know the true process, of course, because I'm simulating it. That's the blue line. We can fit a function, the dashed line, that can approximate our function fairly good. This is a data fitting problem, basically. But a function is nonlinear, so we need those nonlinear bases. And the weights that we calculated are like this. W1, W2, some of them are negative, some of them are positive. You can play with that lambda to see how it will affect this, right? If you change the parameters, you will get different solutions. Now, if you work with deep learning, you could try to build RBF networks to solve the same problem. That's also very interesting.
Are you constrained to having to have the same number of weights as the same number of training points? That makes sense? Like, you need that many to represent the function?
The question is, do we need the same number of weights as the number of inputs? That is a little limiting because, first of all, it's not scalable. This is still a very good method. This is, by the way, it's the second project of Rob 101 course. They fit a surface to precipitation data in Alaska, and then we recover the surface. The true method for regression is a little fancier version of this family of method done by authorities in that state, and they put it publicly available because it's government data. We can access it. So that is used in practice. It's not useless, but it's very limiting because what if I have 100,000 points? The system is going to be super large. We can downsample. That's one solution, right? So you need to pick some basis, right? Every basis you pick, then you need a weight for it. So if you choose to have less weights, that means that you need to cut some of the basis functions. The deep learning variants of it, when you build an RBF network, using modern way of training it, it allows you to deal with many batches. So the number of parameters, they don't have to be in a strong correspondence with the data points you use. So you can play with different sizes of networks and see how it goes. But those networks are, the training is usually they train the centers of the basis functions first, and then you train the weights, and then you iterate over that. So it's possible to use that more general framework to solve this problem. It's a modern way of doing that. But it's not going to use least squares. It's a gradient, stochastic gradient descent solver. Right, this is using the basis that you choose. This is a global solution, whereas the other one will just do a search for you to find whatever that works. Okay.
Professor, I think the reason we're talking about why we need the same size for the n times n+1, that make the whole matrix become underdetermined, right? So that make the problem become not finding the least square problem. Still like that, they still have another extra weighting for phi 0 as a 1. I think that make the problem become not finding the minimum norm for 2 norm. They're just finding the minimum norm for half of the W squares. So I think that's a question that when we expecting for robotics 501 is a little bit different than we solving this problem. Does it make sense? I'm thinking about why he's raising.
Now, I don't teach 501. What can you explain?
Because
what's the problem formulation that is different?
if we have a overdeterminant, they will probably just find us best solutions for AX equal to B.
Mm-hmm.
And however, if you have an underdeterminant,
Right.
The constraint is less than the measurement. So we can't really find the best case for current kind of feeding problem. That's the point that I think.
So you're asking the relationship between minimum norm solution and this problem. So the least squares problem is for overdetermined system. If we're dealing with underdetermined system, we have to talk about the minimum norm problem. The minimum norm problem, this is a quadratic program. You can use off-the-shelf quadratic programming solvers, such as OSQP, to solve this. Because quadratic program has quadratic objective function, linear constraint. However, this particular example has a closed form solution. Not general quadratic programming, but this particular problem, the minimum norm solution will be, still you will get the normal equations. But you have to do phi transpose. So you have to get the other pseudo inverse of the function. Wait. So the solution to the minimum norm problem, instead of, in general, we would write A equals QR for the minimum, and then your solution will be R backslash Q transpose B, right? For AX equals B. For the minimum norm problem, using the same notation I used above, we factorize A transpose to be QR, and then the solution will be Q times R transpose backslash X. So in this particular case, you can solve it, but that's sort of equivalent of what we're doing here. We're using a different narrative here. It's called regularization, and then we have a parameter to play with the relationship between two objective functions. When you add the regularizer, then it's overdetermined again, because we add rows. The right-hand side is 0. but we have rows to say that find the smallest weight close to 0. So these are just different methods we can solve the same problem. So that was just an example. You see that even linear least squares is very powerful. You can solve really interesting problems.
I was just curious. In the above slide, would the matrix inversion lemma help with time efficiency for this problem?
Maybe. The question is, would any matrix lemma help with inversion time efficiency? I guess. That's why people work on these things. The second problem that is our main goal to learn how to solve it is nonlinear least squares problem. So in this case, we are no longer dealing with a residual that has the form of ax minus b, whereas the residual is a nonlinear function of x. So it can be anything that does not have this form. However, if you still minimize the norm of the residual in the same fashion we did, the objective function still defines the least squares problem. In this case, it is nonlinear. So the residual is a vector-valued function that takes an n vector and gives you an m vector. Again, we assume it's a smooth, and it's not necessarily affine. And if it is, then in one step we will recover the solution because it reduces to the linear case. So the norm squared of the residual corresponds to the sum of squares of individual entries of the residual. So each of the entries itself is, of course, a nonlinear function that takes the entire input and gives you a single real number, right? So R is a vector. However, each of them takes the entire input. Which is an n vector and gives you a real number in general, right? In special cases, it might not. If we write the Taylor expansion of one entry of the residual vector, that gives the familiar Taylor expansion of the scalar function. Sorry, it's not a scalar function, it's a single output function, so we get the gradient transpose. If we stack them into a vector, by stacking these gradients as row vectors, we get a Jacobian matrix, right? Which you could do change of variable again and write it in form of D, a delta step. So the Jacobian is stacked version of the gradient for a function that has multiple outputs, right? When the function takes a vector and gives you one real number, you can talk about the gradient. When you have multiple outputs, then we have to talk about the Jacobian because the mapping is from input to a vector, not just one number. So each row is your familiar gradient. Partial derivatives of R1 with respect to all the inputs. The Gauss-Newton algorithm is a method for solving the nonlinear least squares problem. And the algorithm starts with an initial guess. Unlike the linear case, nonlinear problems require an initial guess, because these are local solvers. So we need a starting point, and then continue the search from that point. So for some number of iterations, continue until convergence. In general, there is no guarantee of convergence. So starting from an initial guess, we linearize the residual. So we will have to calculate the Jacobian, right? Once we know the Jacobian, of course, we know the linearization. Then solve a linear least squares subproblem at that iteration, because the linearized form, now this is in an affine form. So we just need to solve the normal equation to find the step size, and then we update the state and continue. Now you might say, why there is a negative sign? Previously there wasn't. Well, because we linearized, there's a sum here, right? When you apply the first order necessary condition, you have to move something the other side, it gets a negative sign. Whereas previously, we wrote ax minus b. When it goes to the other side, it gets a positive sign. So that's why it's like this. So the Newton method uses gradient and Hessian. So to apply the Newton method, which is a second order method, we come up with a quadratic approximation of our objective function around the current guess. So the model M will give us a local quadratic approximation of the function. Then we apply the necessary condition for this approximate model, which leads to solving this linear system of equation. Hessian times the delta of the variable that we want to solve equals negative of the gradient. If the Hessian is well defined, we can invert it or factorize it. We get the step size, and then we update it. So this is different from Gauss-Newton, and we'll point out in the next slide why. For the Newton method, in general, there is no preference for local minima or maxima. It will just find the stationary point. And it's very fast. Near the solution, you had quadratic convergence. There's no preference because depending on the definiteness of the Hessian, you might be dealing with a maximum or minimum. So what's the difference? So you can use both of them to solve this problem. So the difference can become obvious when we look into it this way. The gradient of the nonlinear least squares problem, gradient the objective, the gradient, is Jacobian transpose times the residual. This is 1/2 R transpose R. So the gradient of f, which is partial derivative of f with respect to all the x, is, of course, partial derivative of the residual with respect to x times the residual plus 1/2 of R transpose but to keep it consistent, I think we need to transpose this. So this will lead to and Jacobian is partial derivative of the residual with respect to x. This leads to Jacobian transpose R. So the gradient of the objective function overall as sum of the squares of the residual is Jacobian transpose times the residual. The Hessian is the gradient of, is the Jacobian of the gradient. So if you take the derivative of this term, now you have the same way we follow the Leibniz rule that first derivative times y plus first one times the second derivative. So the first term, when you take the derivative of R, it gives you Jacobian transpose times Jacobian. The second one, that's where the second order derivative will show up because we have to take the derivative of the Jacobian matrix. Whatever it is, that will show you some second order derivatives, and let's call it S matrix. So the Hessian actually can be decomposed into Jacobian transpose times Jacobian plus some S matrix. So in Gauss-Newton, in Newton iteration, where we have Hessian times D equals negative of Jacobian transpose R, Hessian is Jacobian transpose times Jacobian plus S. In Gauss-Newton, we do not calculate the second order derivative. We just approximate the Hessian using Jacobian transpose times Jacobian, which is arguably much simpler. We don't have to calculate the second order derivative. We still benefit from second order like solver result, which makes it very attractive. So Jacobian transpose Jacobian is an approximation of the Hessian. And it's a good approximation because it's always positive semi-definite, whereas S in general can make the Hessian non-PSD. There is no guarantee that you do the exact calculation and your Hessian is positive definite. So if the residual is small, you can expect similar behavior from both methods. And we use Gauss-Newton. We don't use Hessian. So we don't need to calculate the second order derivatives.
So is this kind of running back to your notion of what you said earlier, it's a local solver? So it's one of those things where your initial conditions like far away from what your guess is, and you wouldn't have a good resolution or result of it?
The question is this related to the notion of local solvers and initial guess? No, both of them are local solvers. We're just comparing two methods, Newton and Gauss-Newton. Newton uses the Hessian, the exact second order derivative. Gauss-Newton is a technique that is specifically for the nonlinear least squares problem. And it approximates the Hessian using Jacobian transpose times Jacobian. So Gauss-Newton, you can't apply it to any problem. It needs to be a least squares problem. Newton is more general.
Is there any concern of, well, so because we're saying it's an approximation, so if you're doing sort of many iterations, right, is there any concern of over approximating?
Is there any concern of over-approximating? What does it mean?
Well, like, as a creating approximation of the second derivative, or an approximation of the Hessian, so you might get, you know, incorrect results if that approximation is too far from the theory.
It's possible, not getting the correct answer. We can't fix it. So you have to go back and tune and check what's the problem. So generally, if the problem is well behaved and the loss, like residual that you define, satisfies the assumption that it's continuous and smooth, then starting from an initial guess, you will find the local solution. Now, whether that local solution satisfies your need, that's a different story. In the SLAM, when we find the trajectory, and that trajectory should help us to reconstruct the scene, the local solution might mean that the walls are intersecting and the map is inconsistent. Obviously, that's not good, even though mathematically, well, that's a solution. But it doesn't satisfy our need. We need a local minimum that is sufficiently close to the correct reconstruction and trajectory. That's a challenge in Islam. That leads to current effort in finding global solvers for Islam. There are some progress, but generally speaking, it's difficult. To have the global solver and have it fast online. You can solve it, but it will be probably offline. So that's an ongoing research topic. So let's make the target tracking problem just a warm-up example. Nonlinear. The motion model is the same. The measurement model in this case is its range and bearing. So if I'm going to estimate 2D position with range and bearing, the range is the length of that relative measurement, and arctangent 2 will give me the relative angle with respect to the vertical axis in this case. The Jacobian of the measurement model can be calculated in closed form, and the Jacobian of the measurement model is, of course, trivial because it's linear. So we can stack again the least squares problem. However, when you do it this time, the problem is this Jacobian matrix that we build, B of X. So this linearized system, it will change every time we update the guess. So although you can linearize, we need to evaluate A, left-hand side matrix, and right-hand side at the current guess. Solve the system, take a step, and reevaluate them again. So at every iteration, we have to reevaluate this linear system and solve it until convergence. Some conditions are met. Generally, this is the recipe. Later in the SLAM, we will see that we like to reuse previous calculations as much as possible. Because if we have to solve everything from scratch every time, it's never going to be online. So in a similar fashion, you can construct your residual, calculate the Jacobian. So all you need to do, form the residual, evaluate your Jacobian. The rest is what you see in the algorithm. Once you know the Jacobian, you can solve the Gauss-Newton. So off-the-shelf solvers want the residual and Jacobian usually from you. Then they will solve the least squares problem for you. So in this case, the initial guess we have from range and bearing is very noisy, the green line. And the Gauss-Newton will smooth it and give you the gray or black line. Now, we're fortunate enough that we can use the measurements to actually get a guess of the solution. Sometimes that's even not possible because imagine we only had bearing measurements. But we have it from different angles that we can triangulate. It's not that easy to come up with an initial guess. you might need to try a couple of initial guess or do other tricks to initialize the problem, right? Okay, so you learned the Gauss-Newton. Now, if you see a nonlinear least squares problem, you know how to solve it. And there are many good off-the-shelf solvers. One famous one that is also supported by Google is Cirrus. And in G2O library, which is a SLAM backend, it uses Cirrus solver. In most of the programming packages like MATLAB, languages like Julia and Python, you do usually have a solver for these problems. Okay? Now, you will use another library called GTSAM. That's in your homework 7. You will learn how to work with the API of the library. That will be very useful for your future adventures in SLAM. So now we're going to talk about globalization strategies. Globalization strategies are strategies for global convergence to local minimum. It's a very popular topic in Europe. You hear about it a lot. So in the same line of thinking, we would like to have a set of strategies that enforces global convergence to a local minimum. Doesn't have to be the best solution. At least we can find a minimum, local minimum for the problem. And that really corresponds to one very popular way is to the damped version of the algorithms, which says that don't take the full step and calculate the step size. And this step size, depending on the problem, can be very critical. There are a lot of problems that if you just ignore this step size, there is no convergence. Whereas if you calculate the step size carefully, you get nice convergence. So it can be very important. One nice thing about using libraries for solving your problem is that this is usually handled internally. If you do it yourself, and you ignore this, for particular problems, your solver might work, but in general, it won't be applicable to all problems. So we want to find the step size. The condition is that direction of D is a descent direction. That means that the objective function needs to be reduced when we take a step. In other words, if you take the directional derivative of the objective function along D using this alpha value as the step size of moving along that direction, from calculus we know that that will lead to the gradient transpose times D. It's the projection of your gradient along that direction that you want to move. That's the dot product. It's the differential, directional derivative is the differential of your function along the direction you want to move, not the standard basis of, for example, Rn. And that means gradient transpose times D, which is the dot product of gradient and the direction you want to move. So because of that, D is a descent direction, and if your delta F, right, is less than 0, or the dot product of your gradient with the direction you want to move is negative, then you call D a descent direction. So for direction D, the Newton direction is a descent direction if your Hessian is positive definite. that means the curvature is positive. If it's not, you're not going into a value. For Gauss-Newton, if the Jacobian is full column rank, it's not singular, that will give you a descent direction, because Jacobian transpose Jacobian is guaranteed to be positive semi-definite. You might get zero eigenvalue if the columns are linearly dependent. Other than that, it will be a descent direction, which makes it nicer to use. So the goal is to solve a one-dimensional problem, right? At current step, given a descent direction, solve a one-dimensional optimization problem such that this alpha will minimize your objective function. That's the idea. So you can exactly solve this optimization problem that is called exact line search. Because inside this is a line, right? With different values of the alpha as if you're moving along a line. So it's called line search, and you get exact line search. However, in practice, we do not do exact line search because it can be expensive, but also there's no guarantee that exact line search works better than some heuristics and approximations. The inexact line search is called backtracking. This is one popular algorithm which uses Armijo-Goldstein condition, which is this condition we have here, that the differential of your function, directional derivative of your function, you want this to be negative. So what you can do, you can use this condition and pick define this like this, right? You want this to be negative, right? So this is the condition. So the idea is that pick a large alpha value and backtrack with some factor, 0.9, whatever you choose. Reduce it until you find a good alpha value, right? That's the idea.
With the, so why isn't it that damped, wouldn't that be the opposite of what you want? Because, or like, wouldn't that like make it more easy to get stuck in like saddle points and local minima and stuff like that?
The question is, wouldn't a damped version of the algorithm make it easier to get stuck in saddle point and local minima? Why? Why? That's obvious. That makes it easier.
Well, I guess because if you know you're moving more slowly, that would have an impact on I kind of qualitative, but it's harder to like break free from those forces.
So the only downside here is that we're moving it slower. It can delay the convergence. There's no harm in moving it slower if you're patient. But we want to take the maximum step size that we can. Obviously, instead of iterating 100 times, it's nice if you can iterate 5 times. That will be preferred. So the damped version of the algorithm can increase the number of iterations, which leads to, your question leads to the next strategy for globalization, and it's called trust region methods. I think this will answer your question.
Well, I guess what I was kind of more getting at is, this is just from like other knowledge that there's also, right, like momentum-based.
We're not talking about momentum at all here. So we don't want to bring it into that picture. We can talk about it offline, but it's not related to this discussion. Does that make sense?
Yeah.
We'll be out of time. Yeah?
For the logistic methods, why would you choose a descent direction that's not related?
We do. So the question is, why not choosing the negative of the gradient to be a descent direction? We do, and that is one choice in gradient descent.
Sure, but like, I mean, the way that you wrote the slide with like needing to check if the direction that you chose is in fact the descent direction implies that there might be some cases where you wouldn't choose the negative of the gradient as a descent direction, because you wouldn't have to check if you use the negative of the gradient if you know it's always descent.
The gradient is not the only choice. In general, you can move along any direction in this space. The negative of the gradient is a descent direction. And it is the fastest way of moving to a lower level sets of the function. But again, that doesn't mean it's the best direction, because it is a known behavior of gradient descent that it will zigzag to reach the solution, and that's very undesirable because it takes so many iterations. Whereas you use conjugate gradient, it's a different approach. It will change the direction based on some techniques, duality, dual direction of the gradient, and it will converge, it's guaranteed to converge in n iteration if you have n dimensions. So that shows that the gradient by no means is the best direction to move. It is the obvious descent direction. But in general, you're free to move even randomly, right?
When we're talking about figuring out the best step size, is this something that we do, or do these two steps for the line search, are these things that we do in each iteration? So in each iteration, we figure out what the best is.
Right. In each iteration, you need to find the best step size, because at each iteration, we calculate the new gradient and Jacobian. So we want to know how far we should move. Now, you're not going to do it here in our problems by hand, but generally, it's good to know that inside the solver, something like this is happening. Whereas when you implemented the Gauss-Newton simply yourself, you might not calculate this, right? And if you code it yourself and you see that, oh, when I multiply my steps, each update by a factor 0.2, it's working, but when I'm not doing it, it's not working, then you know it's because your steps are too large. Now, the reason taking larger steps will not guarantee that the objective function will be reduced, minimized, because we are working, remember, we're working with a local approximation of the function. We linearize. Now, how far that linearization or quadratic approximation is valid, that's the question. Maybe if your function is actually quadratic, then it's valid obviously everywhere, right? And the linearization is fairly valid for a good portion of your function. So how far your model, which is not exactly your objective function, is valid when you linearize it at the current step will determine that. The reason in general there is no answer for that because, well, we have to talk about specific objective function or class of function and their behavior. So which makes it very difficult to come up with general rules. One idea to address this problem at the cost of making your solver slower is called trust region methods. Trust region methods, they try to pick a step size delta and condition your local minimization problem using linear systems or quadratic approximation of your function using a constraint that you cannot move beyond this delta region. How much you want to trust your model using this delta region that you have to pick as a distance. So we can quantify, and reevaluate or trust in the model by calculating the actual reduction of your function before and after taking a step divided by expected reduction using the approximate model, linear or quadratic. Now, if this is below a threshold, we should reject that delta movement. Here, D includes the step size that you want to move. It's the direction and the length that you want to move. Below, because if your delta in your function is small, but the model is large, right? There's a discrepancy between your approximation and your actual function. So you don't want that. You want this ratio to be close to each other. The closer they are, the better. So if this is, you pick some threshold, generally they work like this. You pick a delta. If you have to reject it, then you shrink delta because you're at a region that you do not trust your function approximation. And then you keep doing that until slowly you can move to a better region, hopefully. So this is a main idea behind trust region. Of course, there is much more into the actual algorithms. And the way it is that maybe you start from a large delta, right? If you're here, you would pick a large step. But using that quantification, maybe that's not a good idea because there's a discrepancy between the approximation and the model. Then you have to reduce the delta, and then maybe you take a smaller step. Maybe again you take a smaller step until you have maybe a minimum step size that is safe to take. So the Gauss-Newton is good, but the problem is in practice, you might have near singular Jacobian transpose Jacobian, depending on the problem, or sometimes you want to have some notion of trust region in a soft way applied to your problem. Levenberg-Marquardt algorithm will do that for you. So this is a generalization of Gauss-Newton, an extension of that, when instead of just working with the Hessian or its approximation, you add a lambda I, which you remember when we regularized the problem, this popped up in the solution. So larger trust region neighborhood corresponds to small penalty factor, lambda. If lambda is 0, basically there is no trust region. If lambda is if delta is large, that means you're free to move. If you're free to move, there's nothing to regularize. So lambda is very small or 0. If the region is small, that means you're not allowed to move too far, then lambda is large. You're anchoring the solver to don't go too far. You're regularizing it to stay where you are. That's what you're doing. Similarly, there are ideas to update lambda and reduce it at each iteration. The original idea was that Levenberg method was just add lambda I. Marquardt said that let's condition it adaptively based on the diagonal of the Jacobian transpose Jacobian, because as you get closer to the solution, we want to remove this so you can converge faster. Otherwise, the regularizer might delay the convergence. But typically, we call all sort of variations of this Levenberg-Marquardt, or LM, instead of Gauss-Newton.
So I'm kind of confused about the penalty factor that we have, because if we have a smaller delta, then we're not taking as large steps. Correct, but on top of the fact that we're not taking very large steps, now we also have something that penalizes whenever we take large steps, which is already something that's not very likely to happen. So, I guess I'm kind of asking.
So the large trust region, so if you don't have the trust region constraint, right? It's the default algorithm. You can take a step that is very large. What if you regularize your problem? That will not allow you to move that far, right? So having a very large trust region, as if to the extreme case that you don't have it at all, means the lambda is 0, right? And then the opposite, obviously, is that if you shrink delta, that means lambda is large. You're forcing your algorithm to stay around where you are. That will be, geometrically, that's the effect of it. Right, so another.
For the Marquand system, you said that essentially adding, like, instead of identity, adding the diagonal matrix of the Jacobian quadratic term there, essentially that, like, decreases as you get closer to the answer. Did I understand that correctly?
Because the gradient is 0, that's a necessary condition. At the solution,
Okay.
the gradient is 0. The gradient is Jacobian transpose R. Just related to that, right? The derivatives will vanish at the critical point, which is the solution. But it's an idea that you can come up with other ideas. You can also think about it that large lambda will lead to basically, in the limit, it will converge to gradient descent. It will cancel the effect of second order, and small lambda is the Gauss-Newton. That's something you can think about it. Now, to solve the linear systems, ultimately, we have to solve a system of something like this, AX equals B or AD equals B. A is a symmetric matrix. If we have Jacobian transpose times Jacobian, or in Levenberg-Marquardt, we have a matrix like this. Whatever you choose, ultimately we have to solve a linear systems. So again, do not invert A. That's the last thing you want to do. In fact, you should put it in your dating app bio. First thing you want is that makes me laugh. The second thing that doesn't invert matrices explicitly. So two methods that we use are Cholesky and QR. So Cholesky, if you have a triangular system, it's very easy to solve. You can use forward and backward substitution. Again, regardless of whether it's Gauss-Newton or Levenberg-Marquardt, the sub-problem is a linear, it's a squares problem. We're solving a linear systems. If A is L transpose L, call L transpose D Y. First solve for Y using forward substitution, then recover D using back substitution. This is using Cholesky factorization. The QR factorization, or it's called sometimes economic QR, because Q is n by n, but it doesn't give you all the zeros. R is smaller matrix, n by n. Q is an orthogonal matrix, orthonormal matrix, such that Q transpose Q will give you an identity matrix of size n. R is an upper triangular matrix. So if A, D equals B, Q, R, D equals B, Q transpose Q, R, D equals Q transpose B. This is identity, and R, D equals Q transpose B. So in fact, we just need to solve this system using back substitution. So QR makes it very easy to just call a back substitution routine. But what's the difference? So QR does not need, obviously, to form the quadratic form, A transpose A. You can directly work on the Jacobian. Or if you stack the regularizer, it will take this form. It will make A taller. Cholesky works with A transpose A. QR gives you QR for A. QR has a better numerical stability in practice than Cholesky. So if you are concerned with numerical stability, use QR. But QR is slower than Cholesky. Cholesky is faster because it's exploiting the symmetric positive definite structure of A transpose A that will lead to less calculations by exploiting the symmetry of that matrix. The rule of thumb, use QR. Always use QR. You'll be okay. Unless somebody complains that why this is so slow. So, all of this story, the SLAM that we will formulate, will end up having a linear systems. We will face a linear system to solve, and we know how to deal with it. And the initial problem that we formulate, the SLAM problem, the graph SLAM, will be a nonlinear least squares problem. All bundle adjustment in computer vision, all sort of variations of that formulation. We will see how to use this structure and the sparsity of the SLAM to make it fast. So next time, we have to continue this discussion because unfortunately, our parameters for a SLAM evolve in a Lie group. The rigid body transformation is an element of a Lie group. We cannot just use the Gauss-Newton or Levenberg-Marquardt for the Euclidean space for that problem. So next time we try to basically talk about how can we do least squares problem in the Lie algebra. Once we learn that, then we can solve the graph SLAM problem. So that's the reason we have to go one level deeper in the least squares problem. So that's it for today. Next Tuesday, we'll talk about Gauss-Newton on Lie group.